All right, today we want to talk about matrix exponential. So when we have a differential equation like x dot equals to ax, in which this is a vector, n by 1 vector, this is n by n matrix, and this is n by 1 vector again. So we have first order differential equation, but in matrix form. You might think that, well, we have second order differential equation, third order, and all the others. Why we are interested in this one? Because every other differential equations, if it is linear time invariant, we can convert it to this one. And I'm talking about homogeneous. There is no force term here. So let's give an example. Imagine that we have two masses, M1, M2, and then we have spring and damper here. So let's call this K1, K2, K3, and we have damper here, dashpot dampers, C1, C2, and C3. Then if we call displacement of this mass R1 and displacement of this mass R2, then we can write differential equations for this one using free body diagram. I would have M1 R1 double dot plus C1 plus C2 R1 dot plus K1 plus K2 R1 minus K2 R2 minus C2 R2 dot equals to 0. And for the other mass, I would have M2 R2 double dot plus C2 plus C3 R2 dot plus K2 plus K3 R2 minus K2 R1 minus C2 R1 dot equals to 0. So I did some factorization in R1 dot, and we assume that, for example, these two are fixed ends. So now I can write this in matrix form by using state space representation, meaning that I call x1 as R1. I do change a variable, and I call x2 as R2. Then I call x1 dot as, I call x3 as R1 dot and x4 as R2 dot. Why do I do that? Because if you think about it, I'm free to pick R1. I'm free to pick R2. So this can be anywhere, right? While R2 is still, if I fix R1, R2 is still free. So, or I fix R2, R1 is that free. So I call that X1. Then the next one, the next degree of freedom, R2. Then if I think about it, at this, let's say I fix R2 and it is fixed in place, then at this position, it might have different velocities. So if I take a snapshot, I can't assess the status of the system because with the same displacement, it could have different velocities. So that's why this is also free to pick. I can pick different velocity for that position. Now, if I pick this one and this one as the free variables, then R1 double dot is not free anymore because I have to satisfy this equation. So it means that R1 double dot can be written in terms of the other ones, and R2 double dot in terms of the other one. So now I can find X1 dot as X1 dot becomes R1 dot becomes X3. So I want to have everything in terms of X's, no R business now. So X2 dot, I want to see how these would change based on the other variables. So X1 dot, it changes like X3. X2 dot, it would be X4. X3 dot, then it would be R1 double dot, and I have to use this equation. So it would be 1 over M1. And I bring everything to that side, I would have, you see, let's use this first term. So I would have K1 plus minus K1 plus K2, R1, which is X1, minus K2 R2, which is X2, and this is plus because it goes to the other side, K2 X2. Then this term, it is minus C1 plus C2 R1 dot, which is X3. And I have the last term C2 R2 dot, which is plus C2 X4. This is X3 dot in terms of the other one, and X4 dot would be 1 over M2. I don't want to write the terms, then I use this one. So you see, I get X1, X2, X3, X4, all of them, the change in time, X1 dot, X2 dot, in terms of the other x's. So I can write it this way. So I can write X1 dot, X2 dot, X3 dot, X4 dot, as 0, 0. Let's put some distance between them. 1, 0, and then I would have 0, 0, 0, 1, and then I would have x3 dot, it would be 1 over m1, then I have negative k1, negative k2, then k2, then negative c1 k2 over m1, negative c1, negative c2 over m1, and c2 over m1. And for the last row, I would have k2 over m2, and I would have negative k2, negative k3 over m2, and I would have c2 over m2, and I have c2 negative minus c3 over m2, and this times x1, x2, let's have them the same row as the matrix. So x1, x2, x3, x4. So in other words, I got x dot equals to a x. So that is explaining a second degree differential equations, which is time invariant and it is linear. All right. Now let's see how we solve this using matrix exponential. Before that, let's see what is the property of exponential. Just one way that mathematicians came with the idea of exponential was that they thought that, okay, we know that, for example, the derivative of t, let's say we use t, the derivative of t would be 1. The derivative of t squared would be 2t. Derivative of t cubed would be derivative of sine t would be cosine t. So they thought that is there any function that its derivative equals to itself? Then we can think about this function. If I write it as 1 plus t squared over 2 factorial plus t cubed over 3 factorial plus all the other terms, if I do the derivative, then derivative of 1 would be 0. Let's start a little bit earlier, so every term would be underneath its correspondent. So that would be 0, plus derivative of t would be 1. Derivative of t squared over 2 factorial. 2 comes out and down, and it cancels out, and it becomes t. Then this one, 3 comes out and down, and 3 factorial is 1 times 2 times 3. In other words, 2 factorial times 3. 3 cancels out, and it becomes 2 t to the power of 2 over 2 factorial. The next term, t to the power of 4, 4 comes down and out, and it cancels out with the 4 at the end of 4 factorial, so it becomes 3 factorial. So you see, each term is shifted 1 back. So we see that its derivative equals to itself. Now you might think that, okay, what if this becomes infinity? Well, it turns out that for each t, this is a well-behaved function, meaning that it converges. These terms goes to 0 very rapidly because this factorial blows up way faster than this one. So this would go to 0 in such a way that the whole thing converges. So it is well-defined. And when we plug in t equals 1, we get 1 plus 1 plus 1 over 2 factorial, 1 over 3 factorial, and all the other terms. And it turns out to be 2.71 something. And that is not a rational number. And we call that e. So e to the power of t would be 1 plus t squared over 2 factorial plus all the other terms. You can get this from Taylor series when you know that the exponential e to the power of t, the derivative would be just e to the power of t itself. So now if I have e to the power of at, then this would be 1 again plus at plus at to the power of 2 over 2 factorial, and plus all the other terms. When I do the derivative of this one, I would have one a coming out and down. We can use chain rule for that as well. I mean, derivative of a function would be derivative of this times derivative of at itself, which is a then. But we can see that from this series as well. If I do derivative of a, one a is extra because this supposed to make the previous term, right? It would be a squared t squared. 1t would be out, this 2 factor, 1t would be gone, so it would be a squared t over 1 factorial. So it would be this term with 1a extra. So we can factor out a in all terms, and we get a e to the power of at. So the derivative of e to the power of at is a e to the power of at. Why we are using that? Well, let's see why we are doing that. I have to erase this part. All right, now, so if I have just one-dimensional differential equation, let's say x dot equals to ax. This is one-dimensional, not a vector, 1 by 1. And then let's say x at time 0 equals to 0. This is x0. Then, based on that exponential, we can say that x, because that x dot, that should be e to the power of at. So this would be e to the power of at times x0. This would be my x. Y, let's write x on the other side. So x equals to that, right? Because we see that the derivative would be a comes out and down. This is just a number, right? So it would be ax, and at time 0, e to the power of 0 becomes 1. So we would have just x0. So nothing prevents us from defining matrices, this series for matrices, because if you have a square matrix, 4 by 4, 5 by 5, whatever, we can define these terms, right? So instead of 1 in matrices, we have to put I, right? So we can say that we do the same thing for matrices. We have I plus A. By I mean a unity matrix, n by n unity matrix. A plus 1 over 2 factorial, AT, 1 over 2 factorial, t square a cube, a square, plus 1 over 3 factorial, t cube, I can put this up here, a cube, plus t to the power of 4 over 4 factorial, a to the power of 4, and plus other terms. Now, if I do derivative of that, you see, if I do derivative of time derivative of that, this is a matrix multiplied by that t. This is time invariant in our problem. So these are just bunch of numbers. So if we expand them times t, then nothing in those numbers would change. So we can again factor it out. So at the end, we see that the derivative of this, because t is the only thing that it is varying in time, I mean, when we do time derivative, it would be just a. So we would have a, the derivative of this one, plus, remember, it is like that a before. So that a squared doesn't matter. So I would have t to the power of 2. That would come out and down 2 and factor and cancel out. So I would have just t a plus 1 over t squared over 2 factorial a to the power of, by the way, this is power of 2, this is power of 3. Because of this derivative, t cube, the derivative of that, it would be 3t squared, and 3 cancels out, and it becomes 2 to the power of t to the power of 2 divided by 2 factorial times a cube. Then plus this term becomes this term. And we have that a to the power of 4 plus all the other terms. We can factor out a, and then I would have I plus ta plus t to the power of 2, 2 factorial a cube, a to the power of 2 plus t 3 over 3 factorial a to the power of 3 plus all the other terms, right? So I factored out A. You see, because A times I becomes A. A times that, it becomes TA squared. So all the other terms. Now we can call this e to the power of AT. This is a matrix. E to the power of a matrix. This is like a shorthand. There is, I mean, it doesn't have any meaning to have a number to the power of a matrix, but you see, it is the same thing. So we generalize that the notion of exponential, that it can be applied even to the matrices, because this is the same as that. So let's call this e to the power of AT. And we see that if we call this e to the power of AT, then the derivative would be a e to the power of AT. So the derivative of e to the power of AT becomes matrix A times e to the power of AT. So we can use that when we have differential equation like x dot equals to ax, and x at time 0, let's call this x0, some initial values. Then we can use the same thing, because like the previous logic, then we can say that x equals to e to the power of AT times x0. You see the same thing. And because when we do the derivative of that, if this is my x at time t, the derivative of that would be a, the same thing. So the x dot would be ax. And at time 0, it would be e to the power of 0. Then it would be just x naught. You might think that e to the power of a matrix, that it is 0. How come that is becomes 1? Well, again, go back to the definition of e to the power of AT when A is a matrix. If I put 0 here, right? If I put T0, this would go out, 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 everything here. If I put T equals to 0, everything would go out, and I would have just I. I times x0, it becomes just x0. So in fact, e to the power of 0, this time, it wouldn't be 1, it is I matrix, which is I plays the role of 1 in matrices, right? So it would be I times x0, which is 0. So this would satisfy both conditions, I mean, the differential equations and the boundary condition. Now, how can we calculate e to the power of AT? Again, we can go back to the definition. If matrix A would be diagonal, then it would be easy. Why? Because a diagonal matrix, let's say I have A equals to, let's say I have lambda 1, and then lambda 2, and then all the way to lambda n. Then bunch of zeros here, all right? Then A cube, A square would be this time itself. You see this times this, it would be just lambda 1 square. Then the rest, because the rest are 0, the rest is 0. So the second row, the only thing that it is remaining non-zero, it would be lambda 2 to the power of 2. And we would have all the way until lambda n to the power of 2. And bunch of zeros here. So let's erase this part. So we see that I plus AT plus 1 over 2 factorial, it would be just matrix I plus lambda 1t lambda 2t, and lambda nt, bunch of zeros here, plus lambda 1t squared, lambda 1 squared over 2 factorial, lambda 2 squared, t squared over 2 factorial, and all the other terms. So we can see that it would be I plus or 1 plus lambda 1 if we add all these relative terms. If we do matrix addition, then I would have 1 plus lambda 1 t plus lambda 1 t square, this square over 2 factorial plus all the other terms. And the same thing for lambda 2. All the other terms. So, and bunch of zeros. So we can write this as e to the power of lambda 1t, e to the power of lambda 2t, e to the power of lambda nt. So if our matrix is diagonal, because diagonal matrix, the powers of the becomes still diagonal, and if we have a diagonal matrix, all the other terms, for example, it doesn't affect lambda 2, doesn't affect this one. Let's see one example. Let's say I have, for example, 1, 2, 3, and then I have 0, 0, 0, 0, 0, 0 here. This times itself to the power of that, to the power of 2. You see, if we do matrix multiplication, we have this multiplied by this. So we have 1 times 1, which is 1 to the power of 2, right? Then this goes here, and because this corresponding term is 0, and this is 0, this is 0, it remains 0, 0. The same thing for here, it would be again 0. Then if it is multiplied by itself, the transpose of that, then it would be 2 to the power of 2. 0, 0, 0, 3 to the power of 2. So the same thing for higher power. If I multiply it again, if I replace it here, multiply by itself, it would be to the power of 3, to the power of 4. So that's why this term wouldn't affect this term and that term. So they would remain lambda 1. That's why when we have when we have a diagonal matrix, the exponential would be diagonal, and this would go to the power of that, to the exponential power. So it is very easy to deal with exponential of a diagonal matrix. It is also easy if we have a matrix comprising a couple of diagonal matrices. So if I have, for example, A as A1, A2, let's say AN, and bunch of zeros here. And this A is a diagonal matrix itself. So we have a matrix and we have sub-matrices here. So that's to the power of 2. It would be this multiply itself. So it would follow the same way as we did for numbers, except that this time we have a matrix, but a matrix multiplied by the transpose of itself, it would be again the same thing. So this would be A1 to the power of 2, A2 to the power of 2, AN to the power of 2. So we can follow the same logic, and then e to the power of at would be e to the power of a1t, e to the power of a2t. So if we know exponential of a 2 by 2 matrix, all right, and then we have a bigger matrix comprising of those 2 by 2 matrices, then we can make that thing. So if we have a diagonal matrix, it would be the same thing, meaning that if I have A as some matrices on diagonal, then e to the power of at would be e to the power of a1t, e to the power of a2t, and all the other terms. And then it is 0. So if a matrix is made of some other matrices on diagonal, then it would be, if we know e to the power of each one of them, it would help us. So we can write e to the power of at. Why we are saying that? Because while we are talking about diagonal matrices and this type of matrices, because it depends on what eigenvalues your matrices have, then we can diagonalize the matrix depending on if it is real eigenvalues or complex eigenvalues in one of these two forms. So before going into detail of that, let's look at e to the power of at again. E to the power of at is I plus, remember, at plus 1 over 2 factorial. This t can be here or there because it is just a scalar, right? So a cube, I put t here, plus t cube over 3 factorial a cube. So, I mean, sometimes I might put it there or back because it is just a number, let's say. So now, if I have, let's say, my A, I write it as, there is some matrix that I can write it as P inverse, then let's say D, P, all right? There is a P that is invertible that I can write my A as P inverse DP. Let's say there is such a P that I can write it that way, right? So now if I calculate A square, it would be P inverse DP times P inverse DP. And this P inverse, P inverse, it becomes ID becomes D. Then I can write this as P inverse D square D, right? The same thing for if I multiply again by P inverse DP, that P inverse P, it would cancel out and becomes I, then it would be D cubed. Then d to the, so I can write any power as P inverse d to the power of n p. Because you see, if I do again, if I do a cube now, then I would have P inverse d square p, then again P inverse d p. And these two would be I, then ID would be I, so I would have one more power for D. So it would be P inverse D to the power of 3P. So I would have this generally by induction to the power of N. Then if I plug in all these, I would see that e to the power of AT equals to I. And instead of I write it as P inverse P because it is the same thing, right? Or let's say P inverse IP. Instead of I write it that. Then A would be P inverse D P T plus T square over 2 factorial. Then instead of A square, I write it as P inverse D square P. And all the other terms. I can see, I can factor out P inverse from the left, and P from the right. So inside it would be I plus D plus T square over 2 factorial D to the power of 2 plus T cube over 3 factorial D to the power of 3 plus all the other terms, and I factored out P from that side. So I factored out P from left, P inverse from left, and P from the right. Then this would be e to the power of D. So I can write it as P inverse e to the power of D T P. So this is very good. If I have A as P inverse D to the power of P, e to the power of AT would be P inverse D to the e to the power of DT. You see, that P, it's like it doesn't do anything. If I have that e to the power of AT, I can have e to the power of DDT, right? And P inverse. So you see, if I write my A this way, then I can say e to the power of AT equals to this. So if A is that, e to the power of AT, the same thing. I just powered e to the power of DT here. See these two, compare these two. So now why we are interested in this relation, because we can diagonalize D, meaning that if I have A, I can find P inverse and P such that this would be diagonalized. So instead of calculating e to the power of AT, I calculate e to the power of a diagonal matrix because we saw that it is easy. And then we do this P inverse and P again. So again, let's see the importance of that. If I have A and it is not diagonal, let's say it is 10 by 10 matrix, it is difficult to calculate all the powers and make it e to the power of AT. So instead, I can diagonalize. I find the diagonal matrix such that it satisfies that. Then that diagonal matrix calculating the power e to the power of that diagonal is very easy. Then I can just multiply it by 2 matrix and I get e to the power of AT. All right. So that is the topic of another video, that how to diagonalize a matrix when that matrix has distinct real eigenvalues and when it has complex eigenvalues. That would be another video. But for that damper system, the mass damper system, 2 masses and 2 damper, that it was at the beginning of this video, I solved it in Matlab at the end of this video. I solved it with just matrix exponential of the Matlab just to see the results. All right, so there would be another video that explain how to diagonalize the matrix. But now we see that if we have a matrix that we can diagonalize, then it would be easy to calculate e to the power of AT of that. And that solves the differential equation when we have x dot equals to AX. All right, this is the MATLAB code, live script, MATLAB version 2023A. For 2 degrees of freedom system. By the way, I put this code at the end of the, on the bottom of the YouTube video. So you can see that and run it in live script yourself. So the displacement of mass 1 is represented by R1, and for mass 2 it is R2, and we have 3 springs and 3 dampers. Then we define those values and we use the state space representation, meaning that we define displacement and velocities as independent variables. So we get a 4x4 matrix, as we explained at the beginning of the video. Then this I command in MATLAB, it gives out both the eigenvalues and eigenvectors. When we use it this way, it puts the eigenvalues on the diagonal of a 4x4 matrix. and it stacks eigenvector U's next to each other. So when we showed that U inverse times A times U should give out a block diagonal matrix or a diagonal matrix when the eigenvalues are real and distinct. And as we can see, U inverse AU, it is that 4x4 matrix, and the eigenvalues are on diagonal. So it is the same as this one, except probably you see that there is a -0 here, because probably this is a numerical error, and numerical, stuff that happens. And it is probably, for example, 8th digit is a number, and it is very close to 0. So for all that we care, it is the same. These two are the same. So now, we can define diagonal of A as matrix exponential. This is the command that we use for exp of a matrix in Matlab, expm. So matrix exponential of, so in a sense, it is e to the power of lambda t, that lambda matrix lambda t. So this is the matrix e to the power of dt in our video. So when e to the power of that diagonalized matrix, then we have to multiply it by U from the right and U inverse from the left, and then multiply by X0, it gives us X at any time. And you see, it is a sort of complicated function. It has all 4 exponentials for each one of the x1, x2, x3, x4. Don't forget that x1 is r1, the displacement of mass 1. Displacement of mass 2 is x2. Then this is the velocity of mass 1. So x3 is the velocity of mass 1, or r dot, r1 dot. Then this is in symbolic form. So we define t to go from 0 to 250 millisecond, or 0.25 second. Then we do the eval command to evaluate that output at these t's. And then we plot it. So we call it output plot, and then we plot it. We know that for a system with damper, ultimately both all the displacements and the when there is no external forcing, so all the displacement and velocity should go to 0. And this is what we see, that all of them will go to 0 after some time. And they have initial values, but ultimately they all go to 0. And because all the eigenvalues are real, so there is no oscillation here. And that was by purpose. All right.